All right, today we're going to continue solving second-degree trig equations, but we're going to perform some substitutions. And the reason we're going to perform some substitutions is because of the existence of two different trig functions within the equation. So if we take a look at this, we have a cosine squared, and we have a sine. So the previous video, what we had was all sine squared, or all sine function, all cosine functions, all tangent functions, they're all the same. In this case, they're different, so we're going to have to manipulate this. And the way we're going to do it is with Pythagorean identities. Two important prerequisites to this video is Pythagorean identities and solving second-degree trigs. So if you're uncomfortable with either of those, I would recommend you watch them again. But knowing both of those informations, let's see what we can do with the cosine squared. We know that sine squared plus cosine squared equals 1. So now your cue to change the cosine squared is this right here. Your first degree function leads you to believe whatever function you want existence in the entire equation. So since we have a sine theta, we have no other way to express sine theta. The only other way to express sine theta is with its reciprocal function. And that's not going to help here. So we need a Pythagorean identity for our cosine squared. Just remember, Pythagorean identity comes from the Pythagorean theorem, a squared plus b squared equals c squared. So they're only for second degree functions can you substitute. So now what we want to do is express everything in terms of sine. So what I'm going to do is use my Pythagorean identity and solve for cosine squared and plug in an equivalent value. So if I subtract sine squared from both sides, I end up with cosine squared equals 1 minus sine squared. So now what this is telling me is that 1 minus sine squared can be plugged in to cosine squared. So I can express this equation as 2 times whatever cosine squared is equal to minus sine equals 1. We already found out that cosine squared is 1 minus sine squared. And there's my substitution. Now I'm going to solve this the same way I did with regular second-degree trig equations. So let's move forward with this. We said that cosine squared is 1 minus sine squared. And the reason I knew to substitute for a sine function was the first degree. My first degree term was sine, therefore I want everything to be sine. Another important thing, make sure you're using parentheses to plug in so it reminds you to distribute the 2. So let's distribute the 2 here. We get 2 minus 2 sine squared theta minus sine theta equals 1. And now we'll get it into standard form. Let's subtract 1 from both sides and put it in descending order. Whoop, negative 2 sine squared, not cosine squared. Negative 2 sine squared. When we subtract 1, minus sine. And when we subtract 1 from both sides, we're going to have a positive 1. Lastly, if you recall back to solving quadratics, if we had something like negative x squared minus x plus 1 equals 0, we multiply the entire equation by negative 1, even if there is a low leading coefficient. We multiply the whole equation by negative 1 to give us a positive value of x squared. So now what I'm going to do, I'm going to factor this, because that's going to help me factor this. So let's multiply everything by negative 1, giving you 2x squared minus plus x minus 1 equals 0. So there's a leading coefficient of 2, so let's use the payback method to factor. Multiply the leading coefficient into the last term, giving you x squared plus x minus 2 equals 0. Let's factor this normally. X plus 2 and x minus 1 equals 0. We borrowed the 2, now we're going to divide both numbers by it. Keep any division. 2 divided by 2 is 1, and the other goes in front, so we have 2x minus 1. So these are the factors of that. I'm just going to express it in terms of sine and not x. So what this turns out to be, sine theta plus 1, instead of x, we're just putting sine, times 2 sine theta minus 1. Okay, so I factored it like a regular polynomial, like a regular quadratic, and then I converted it back to a sine function. Just makes it a little easier because this is something we're a little more comfortable with. So, The point of this was just a factor. We're done, so let's get rid of it. So now we have two factors. Let's set them both equal to 0 and solve separately. So sine theta equals -1. And 2 sine theta equals 1. I set it equal to 0 and I subtracted 1. I set it equal to 0 and I added 1. So we have sine theta equals 1/2. So now this side, when you're working with 1 zeros and -1s, just refer directly to the unit circle. Sine is the y-coordinate. The y-coordinate here is -1. The y-coordinate is -1 right there only. So for this side, for sine theta equals -1, we get our angle is 270 degrees. For this side, for sine theta equals 1/2, before we take the inverse sine of 1/2, we're going to identify which two quadrants is sine positive. Sine is a positive number. Both sides positive there and there. All students. Let's take the inverse sine. The inverse sine of 1/2 will give us our reference angle. So our angle in this case is 30 degrees. But remember, that's only our reference angle. Well, that's our first quadrant angle. But we also want to put 30 degrees into the second quadrant. This is 180. We're 30 before it. So our other solution is 150. Now in this case, we only have 3 solutions. We have a maximum of 4 solutions, 2 per linear equation. You can see here that sine only reaches -1 once. That's why we have 3 solutions instead of 4. What we'll have to do now is make sure that they wanted degree measure as our answer by looking at the domain given. The original question gave us a domain of 0 to 360 using 0 and not 360 if you were to get one of those solutions. So this is our cue saying that they want a degree measure, so we do not need to adjust this. If this number had said 2 pi, well then I would have to convert my degree measures to radians. So the approach wouldn't change, the way in which you provide your answers will. So you'd have to multiply your answers by pi over 180 here. But we're looking for degrees, so we're good. All right, here's another example. So now we have 4 sine squared plus 4 cosine equals 5. Our first degree function tells us we want everything to be that. We want everything to be cosine in this case. We can't change cosine, but we can change sine squared. And the way to change sine squared is by using a Pythagorean identity. The Pythagorean identity using sine and cosine is sine squared plus cosine squared equals 1. If we want to substitute for tangent or secant or cotangent, we would have to divide all 3 terms by the same second degree function. So let's make everything cosine, which means we want to solve for sine theta to see what it's equal to. So in this equation, we're going to get sine squared on one side and then substitute for it. So that means we're subtracting cosine squared. Sine squared equals 1 minus cosine squared, which says that this is that. So we're just going to plug it in. Make sure you're using parentheses to remind yourself to distribute. So let's use some parentheses here and open up 4 times whatever sine squared is equal to plus 4 cosine equals 5. And we found out that sine squared is equal to 1 minus cosine squared. Now let's distribute the 4. 4 minus 4 cosine squared plus 4 cosine equals 5. Now that we have all cosines, we can begin factoring if it's factorable. There is a chance that you can have an unfactorable quadratic in which you have to complete square use the quadratic formula. So let's get it into descending order. -4 cosine squared plus 4 cosine, and we're going to subtract 5 from both sides, giving us a -1 equals 0. So now I'm going to make this an x squared term just to make it a little easier to factor. My quadratic would be -4x squared plus 4x minus 1 equals 0. So let's multiply everything by -1. 4x squared minus 4x plus 1 equals 0. And now let's use the payback method. We're going to borrow the 4, multiply it into the last number, giving us a quadratic of x squared minus 4x plus 4 equals 0. Let's factor this normally. This has factors of x minus 2 and x minus 2. We borrow the 4, don't forget to pay it back. We're going to simplify both fractions to x minus 1/2 times x minus 1/2 equals 0. Now both denominators go in front of x, giving you two equal factors of 2x minus 1 times 2x minus 1. So that's what's going to be, not x, cosine. So not 2x minus 1 to cosine minus 1. Not 2x minus 1 to cosine minus 1 equals 0. So now that we have factored, this work is useless. It's just to help us factor that quadratic, a trigonometric quadratic. So now we're going to set both of these equal to 0 and solve separately. We get 2 cosine theta equals 1, 2 cosine theta equals 1, and now we have the same equation, so really we're only solving one of them, because by solving one, we've indirectly solved the other as well. So let's divide by 2. That tells us that cosine equals 1/2. And now before we find the inverse cosine of 1/2, let's identify which two quadrants we are looking for solutions in. Cosine is positive. Well, cosine is positive in the first and in the fourth quadrant. So we're looking for first quadrant angle and the fourth quadrant angle. By taking the inverse cosine of 1/2, we're finding our reference angle. The inverse cosine of 1/2 is 60 degrees. So this is 60 and this is 60. Down and up. Well, if this is 360 and we're 60 before it, our other solution is 300. So those are our two solutions. Only two solutions here, because we ended up with identical quadratic factors. Last example. Now in this case, we have 2 sine equals cosecant. Not a second degree function. We cannot use Pythagorean identities because nothing's being squared. But we do have reciprocal identities. Cosecant is equal to 1 over sine. Well, let's put this over 1, and now we'll remind us to cross multiply. 2 sine times sine is 2 sine squared, and cross multiply equals 1. So now we'll divide by 2 and take the square root of both sides. Sine squared is equal to 1/2. Take the square root of both sides. Sine equals positive and negative radical 1, which is 1, over radical 2. After rationalizing your denominator by multiplying by radical 2 over radical 2, you'll get sine is equal to positive and negative radical 2 over 2. Well, that's a special right triangle value that you should be familiar with, but the existence of a positive and a negative is telling us that we're looking for solutions wherever sine's positive there, sine's positive there, and where sine is negative. Well, sine's negative here, and sine's negative here. So we're looking for a solution in all 4 quadrants with the same reference angle. The inverse sine of radical 2 over 2 is 45 degrees. So we want to put 45 degrees in the first quadrant, 45 degrees in the second quadrant, 45 degrees in the third quadrant, and 45 degrees in the fourth quadrant. So not only do we get solutions of 45, second quadrant, this is 180, 45 before that, 135. Well, this is 180, 45 after that, 225. And this is 360, 45 before it, 315 degrees. So there are our 4 solutions. Most important part about this question, don't forget, when you take the square root of a number, it can be positive or negative.